Whispers in the dark, unveiling our galaxy's hidden stars. Look up at the night sky. We see the familiar constellations, the pinpricks of light we've known our entire lives. But what if I told you that for every star you can see with your naked eye, there are millions more hiding in plain sight, stars so strange, so powerful, and so ancient that they challenge everything we thought we knew about our own galactic neighborhood? Tonight, we will journey beyond the familiar and explore a few of the universe's most extraordinary celestial secrets, the hidden stars that populate our Milky Way. We'll pull back the cosmic curtain on 4 of these fascinating stellar bodies: the enigmatic runaway stars, the ancient relic stars, the explosive vampire stars, and finally, the colossal supergiants that are much closer than you think. So, let's begin our journey with the most dynamic and dramatic of our hidden stars, the runaways. When we think of stars, we usually picture them sitting comfortably in their constellations, part of a peaceful, celestial family. But that's not the reality for these cosmic outcasts. Imagine a star not gently drifting through space, but being violently ejected, hurtling away from its birthplace at speeds that are almost impossible to comprehend. These are the runaways. They're like celestial rebels, moving so fast, sometimes up to 2 million miles per hour, that they can actually escape the gravitational pull of their home galaxy and venture into the vast emptiness of intergalactic space. But how does a star get so much energy? There are 2 primary ways a star becomes a runaway. The first is the most common and perhaps the most violent, a supernova explosion. Most massive stars exist in binary systems, with 2 stars orbiting each other. When one of these stars reaches the end of its life, it goes out with a bang, a spectacular supernova. That incredible explosion can be so powerful that it acts like a cosmic cannonball, launching its companion star out of the system at tremendous velocity, sending it rocketing through the galaxy alone. It's a lonely, high-speed journey born from a catastrophic farewell. The second way is even more dramatic and far more terrifying. This happens when a star gets too close to the supermassive black hole at the center of our galaxy. Imagine a star cluster orbiting a black hole. When a star ventures too near, the black hole's immense gravity acts like a cosmic slingshot. It grabs the star, whips it around, and then flings it away with such force that it achieves escape velocity. This isn't a gentle push, it's a gravitational whipcrack that sends the star hurtling toward the edge of the cosmos. Why do these runaways matter? They are much more than just cosmic curiosities. For astronomers, they are invaluable tools. By tracking their trajectory, where they came from and where they're going, scientists can actually map the distribution of matter and dark matter within our galaxy. A runaway star is like a pinball in a galactic pinball machine. Its path tells us about the invisible forces and gravitational fields it encountered along the way. They are literally leaving a trail that helps us understand the hidden gravitational architecture of the Milky Way. They are the first clue that our galaxy is far more violent and dynamic than its tranquil appearance suggests. And now that we've glimpsed the high-speed drama of the runaways, let's travel back in time to the very beginnings of the universe and uncover our next hidden star, the ancient and silent relic stars. We've just witnessed the high-speed drama of the runaways, the cosmic rebels. But now, let's slow down and journey to a very different kind of hidden star, one that is not defined by its speed but by its ancient, quiet existence. We're going to talk about the relic stars, the cosmic fossils of our galaxy. When we look up at the night sky, every single star we see, including our own sun, is a product of galactic recycling. They are stars that have formed from clouds of gas and dust that have been enriched by the spectacular deaths of previous stars. Every element on the periodic table heavier than helium, from the carbon in your body to the iron in your blood and the gold on your finger, was forged in the fiery heart of a star that died long ago. Our sun is a metal-rich star because it contains the cosmic shrapnel from countless stellar explosions that came before it. It's a second or third generation star, built on the legacy of its predecessors. But what about the stars that came before all of that? The very first stars? They didn't have any of those metals to work with. When the universe was born, it was almost entirely made of just 2 simple elements, hydrogen and helium. So the first stars were built from this primordial, pristine material. And those are our relic stars. They are the living echoes of the cosmos's infancy. Their chemical composition is almost purely hydrogen and helium, with trace amounts of heavier elements, a fingerprint that marks them as being born from the very first moments of star formation. Finding one of these stars is like discovering a time capsule from the universe's beginning. It's a pristine artifact that tells us what the galaxy looked like before the great age of stellar forging began. They are the living echoes of the cosmos's infancy. Their chemical composition is almost purely hydrogen and helium, with trace amounts of heavier elements, a fingerprint that marks them as being born from the very first moments of star formation. Finding one of these stars is like discovering a time capsule from the universe's beginning. It's a pristine artifact that tells us what the galaxy looked like before the great age of stellar forging began. Think of it like an archaeological dig. Most of what we find are artifacts from more recent civilizations, buildings, tools, and art that have been shaped and refined over time. But every so often, an archaeologist finds something truly ancient, something untouched by later generations. A simple, rough-hewn tool from the earliest days of human civilization. That's what a relic star is to us. It is a humble, ancient tool that reveals the conditions of the cosmos when it was in its infancy. These stars are a quiet testament to the story of our universe. They are hidden not because they are small or fast, but because they are so faint, so rare, and so far away in the distant halo of our galaxy, patiently holding the secrets of a time that we can no longer see. They are a profound reminder that our galaxy is not a static place, but an evolving story, with chapters that are still being written and chapters that have long since passed. But not all stars are content with simply being a footnote in history. Our next hidden stars have found a way to cheat death itself. We're going to talk about the most deceptive and mysterious stars of all, the vampires of the cosmos. Our Sun is a metal-rich star. Its composition is filled with the cosmic leftovers of a previous generation of stellar explosions. But a relic star? They have almost no metals at all. They are nearly pure hydrogen and helium. Think of it like this: if our Sun is a master chef with a full spice rack, a relic star is a first-time cook with only salt and pepper. And that's what makes them so profoundly important. They are time capsules. Finding one of these stars is like discovering a pristine library from the early universe. By studying their composition, astronomers can learn about the conditions of the cosmos when it was in its infancy, what the first nebulae looked like, how the first stars formed, and how the first galaxies began to take shape. They are literally the living history of our cosmic origin story, floating silently in the darkness. These ancient stars are hidden not because they're fast, but because they are so faint and so few. We're only now, with powerful new telescopes, beginning to find them in the Milky Way's halo, the ghostly sphere of stars that surrounds our galaxy. They are a testament to our galactic past, a quiet, humble reminder of where we came from. But not all stars are content with simply fading into history. Our next hidden stars have found a way to cheat death. We're going to talk about the most deceptive and mysterious stars of all, the vampires of the cosmos. We've looked at the galaxy's most ancient residents, the relic stars, but now, let's turn our attention to something truly bizarre: stars that defy the aging process. Stars, just like living things, follow a predictable life cycle. They are born, they shine for billions of years, and then they eventually die. But in the deep reaches of our galaxy, astronomers have found a population of stars that are cheating death. They appear young and vibrant when all evidence suggests they should be old and dim. They are what astronomers have playfully dubbed the vampire stars. Formerly known as blue stragglers, these stars are an astronomical paradox. In a star cluster, all stars are born around the same time. You'd expect to see a full range of stellar ages: young, blue, massive stars that will burn out quickly, and older, dimmer, red stars that have been around for billions of years. But every so often, astronomers spot an odd one out, a star that is much bluer and brighter than its neighbors, as if it's a youthful outlier in a retirement community. This is a vampire star. So, how do they do it? The secret lies in a dark and dramatic process. Unlike our Sun, most stars in the galaxy are part of a binary system, with two stars locked in a gravitational dance. Sometimes, if these stars are close enough, the larger, more massive star becomes a cosmic predator. As its smaller companion begins to age and expand, the larger star uses its immense gravity to literally siphon off the hydrogen fuel, the lifeblood, from its partner. It's a stellar feeding frenzy. Imagine it, the larger star is essentially stealing youth. The influx of fresh, hot hydrogen revitalizes it, making its core burn hotter, brighter, and faster. It becomes a blue straggler, appearing as a young, energetic star, while its partner is slowly drained of its life and fades into obscurity. The vampire star is a star that has found a way to rejuvenate itself at the expense of its companion, and this cosmic act of piracy is one of the most remarkable and unexpected processes in stellar evolution. The discovery of these vampire stars wasn't just a curiosity, it was a profound challenge to our understanding of how stars work. For decades, astronomers were mystified. They just didn't make sense. But once we understood this bizarre process of stellar vampirism, it opened up a whole new field of study. These stars are living evidence of just how complex and violent the cosmos truly is. They show us that stars don't always follow the rules, and that in the dense, crowded environments of star clusters, they will do whatever it takes to survive, even if it means consuming their neighbors. These blue stragglers are hidden in plain sight, masquerading as young stars in ancient stellar communities. They are a testament to the fact that not everything is as it seems in the night sky. And while some stars are busy cheating death, others are on a completely different scale of existence. They are not merely stealing youth, they are the grand, slow-moving titans of the galaxy, so colossal that they are hidden by their own sheer size. But what happens on the other end of the spectrum? What happens when a star-forming cloud of gas and dust just doesn't quite make it? This brings us to our next hidden star, or perhaps, the ultimate anti-star, the brown dwarf. Astronomers often call them failed stars, and it's a fitting nickname. Brown dwarfs are celestial objects that sit in a strange middle ground between a star and a planet. They are too massive to be considered a planet, but they don't have enough mass to ignite the hydrogen fusion that makes a star shine. Our Sun and every star in the night sky are powered by a constant, stable nuclear reaction in their core, fusing hydrogen into helium. A brown dwarf never reaches that milestone. Instead, a brown dwarf only has enough gravity to briefly ignite a much weaker fusion reaction, involving a heavier isotope of hydrogen called deuterium. This weak fusion only lasts for a short period, a few million years at most. After that, the brown dwarf spends the rest of its existence simply cooling down, slowly radiating away the residual heat from its formation. As it cools, it grows dimmer and dimmer, fading from a faint reddish glow into a cold, dark, and almost invisible object. This is precisely why they are so hidden. They don't emit much visible light. While a young, hot brown dwarf might glow a dull magenta or a deep red, a truly old one becomes a ghost in the darkness. We can only find them using specialized infrared telescopes that can detect their faint heat signatures. Imagine a star that you can't see with your eyes, but you can feel its warmth from across an unimaginable distance. That's a brown dwarf. They are also incredibly common. Recent surveys suggest that there may be as many brown dwarfs in our galaxy as there are stars. They are the silent, hidden majority of our cosmic neighborhood. Their existence challenges our simple classifications, blurring the line between star and planet and forcing us to reconsider the very mechanics of how celestial bodies form. They remind us that the universe is not just about the spectacular and the brilliant, but also about the faint, the failed, and the almost there. The study of brown dwarfs is a relatively new field, and every new discovery of one of these substars offers us a glimpse into a hidden population of objects that may hold the keys to understanding a crucial link in the chain of stellar evolution. They are the quiet evidence that not every cosmic journey ends with a bright destination. But if a brown dwarf is a star that failed to ignite, what happens when a star burns so brightly that it detonates itself and leaves nothing but a tiny, dense corpse? That's what we'll explore next. We have just explored the brown dwarf, the star that failed to achieve greatness. Now, let's talk about a star that achieved it and then some, burning so brightly and ending so spectacularly that what was left behind is something truly alien. I am talking about the tiny, terrifyingly dense remnants known as neutron stars. To understand a neutron star, you have to imagine a star much more massive than our Sun, one that has reached the end of its life and gone supernova. That immense explosion blasts away the outer layers of the star, but it also triggers an incomprehensible event at the core. The core collapses under its own gravity with such force that protons and electrons are squeezed together into a solid mass of neutrons. It's a cosmic crush that is almost beyond our ability to imagine. The result is a star with an incredible secret: it is unbelievably small and unbelievably dense. A neutron star has the mass of 2 or 3 of our suns, but it's all compressed into a sphere no larger than a city, maybe 12 miles across. To give you a sense of that density, if you were to take just a single teaspoon of neutron star material, it would weigh over 1 billion tons. That's more than the weight of every car, truck, airplane, and ship on Earth combined. It is matter pushed to its absolute physical limit. So how are these stars hidden? You can't see a 12-mile wide star from light years away. They are far too small and faint to be observed directly. But some of them have an incredible feature that acts like a cosmic billboard. These are the pulsars. As the neutron star collapses, its magnetic field gets squeezed, becoming billions of times more powerful, and its rotation speeds up to an unbelievable degree. It can spin hundreds of times per second, faster than the blade of a helicopter. This powerful magnetic field, combined with the rapid spin, creates a beam of electromagnetic radiation shooting out from each of its poles, much like a lighthouse. This is the key to how we find them. A pulsar is hidden from us unless its rotating beam of light sweeps across our solar system, causing us to see a regular, flashing pulse. For years, scientists were mystified by these perfectly regular, ticking radio signals until they realized they were hearing the distant, rapid heartbeat of a neutron star. These tiny titans are invaluable to us. Their incredible regularity makes them the most precise cosmic clocks we know, more accurate than our atomic clocks on Earth. Scientists use them to study the fabric of spacetime and to test Einstein's theories of relativity. They are also laboratories of extreme physics, allowing us to study matter under conditions that we could never hope to replicate here on Earth. But even a neutron star is not the end of the line for cosmic extremes. What happens when a neutron star's magnetic field becomes a force so powerful that it can tear the very atoms out of your body from a quarter of the way across the galaxy? We'll explore that next. Exist objects in the universe, with magnetic fields that are billions of times stronger than our own. But in the vast and violent tapestry of our galaxy, there are a few of these objects that take that power to a scale so extreme, so incomprehensible, that they challenge the very fabric of reality. I am talking about magnetars, the powerhouses of the cosmos. A magnetar is a type of neutron star, but with a difference that defines it completely: its magnetic field is thousands of times stronger than a regular neutron star. To put that in perspective, a regular refrigerator magnet is strong enough to hold a piece of paper. The Earth's magnetic field, which protects us from solar radiation, is 1,000 times stronger than that. A neutron star's magnetic field is billions of times stronger still. But a magnetar? Its magnetic field is trillions of times stronger than the Earth's. It is the most powerful magnetic force known in the entire universe. This isn't just an academic number, it's a force with destructive power on a galactic scale. If a magnetar were located a quarter of the way across the galaxy, its magnetic field would be strong enough to erase every credit card on Earth. From just 600 miles away, it would be strong enough to rip the atoms right out of your body. So why are these colossal powerhouses hidden from us? Their extreme magnetic fields are in a state of constant, immense stress. The magnetic field lines are stretched and tangled by the magnetar's rapid rotation. Every so often, that tension becomes too great, and the magnetic field lines snap and reconnect in what scientists call a starquake. This magnetic reconnection releases an incredible burst of energy, called a soft gamma repeater or an anomalous X-ray pulsar burst. The energy from a single one of these bursts is so powerful that it can be brighter than an entire galaxy for a few hundredths of a second. This is how we find them. A magnetar is like a dormant volcano, it's hidden and quiet for long stretches, but every so often it gives off a spectacular, explosive outburst that reveals its terrifying power. These rare and brief outbursts are what make them a key focus for astronomers. Magnetars are cosmic laboratories that allow us to study physics under conditions we could never replicate. They push the boundaries of our understanding of matter, gravity, and magnetism to their absolute breaking point. But not every star is bound to a galaxy. Our next hidden stars are the ultimate loners, living in the quiet, empty void between galaxies. They are the stars that were once part of our celestial family, but are now forever lost. We have explored stars of immense power and extreme density. But for our next hidden star, we're going to leave the comfort of our own galactic home and journey into the ultimate cosmic frontier, the vast, empty darkness between galaxies. Here, we find the lonely and mysterious extragalactic stars, also known as intergalactic stars. For most of human history, we thought that all stars belonged to a galaxy, held in place by its immense gravitational pull. Galaxies were the cities of stars, and the space between them was a cosmic no man's land. But recent discoveries have revealed that this is not the case. There are billions, perhaps even trillions, of stars that have been violently ejected from their home galaxies and now drift, silent and alone, in the cold, black void of intergalactic space. They are the ultimate cosmic exiles. So, how does a star escape its home galaxy? The most common way is through a catastrophic event involving a supermassive black hole. A star can be part of a binary system that wanders too close to the black hole at the center of its galaxy. The black hole's immense gravitational pull can rip the binary apart, consuming one of the stars and flinging its companion away at such an incredible speed that it is slingshot out of the galaxy forever. Another way is through galactic mergers. When two galaxies collide, their gravitational fields are in a state of chaos. This cosmic pileup can result in stars being flung out of their home galaxies at velocities that defy comprehension, sending them on a one-way trip into the cosmic abyss. It's a spectacular and violent event on a scale that is almost impossible to grasp. And this is precisely what makes them so hidden. These stars are alone, with no galactic neighbors to provide a backdrop of light. Imagine looking for a single candle flame on a dark night from 100 miles away. That is what trying to find these stars is like. They are separated from us by millions of light-years of empty space, making their light incredibly faint and their detection a monumental challenge. It's a testament to the power of our modern telescopes that we can find them at all. But why do we look for them? Because they are more than just cosmic curiosities. They are the breadcrumbs of galactic history. By studying where they are, how fast they are moving, and what they are made of, scientists can retrace the history of galactic mergers and map the invisible web of dark matter that holds the universe together. The extragalactic stars are living evidence of our universe's violent, dynamic past. We have now traveled from failed stars to the galactic exiles. We have explored the limits of known matter. But what if we've only scratched the surface? What if there are stars out there that are even more exotic, even more extreme, than anything we have yet discovered? That brings us to our final hidden star, one that may not even exist at all. We have journeyed to the limits of what we know, to stars that have been cast out from their home galaxies. But what if there are stars out there that are so extreme, so dense, that they are made of a form of matter that we have never observed? We are now entering the realm of the truly theoretical, where the universe's ultimate hidden star may not even be a star at all, it's a quark star. To understand a quark star, let's briefly revisit the neutron star. We learned that a neutron star is an object so dense that its protons and electrons have been crushed into a solid mass of neutrons. It is matter pushed to its limit, or so we thought. But physicists know that even a neutron is not a fundamental particle. Inside every neutron are even smaller particles called quarks. The theory of a quark star asks a profound question: what if the gravity in a star's collapsing core is so immense that it overcomes even the force holding neutrons together? What if the neutrons themselves are crushed, dissolving into a sea, or a soup, of their constituent quarks? This would be a new phase of matter, a type of cosmic dematerialization, where all of the structure we know is stripped away, leaving only the fundamental building blocks of the universe in a single, ultra-dense object. The existence of a quark star has never been confirmed. It is a star that is hidden not by dust, not by distance, and not by a strange life cycle, but by the very limits of our scientific understanding and technology. They are a hypothetical final stage for the most massive and violent of supernovae, the cosmic version of a final, crushing blow. So how would we find them? Some scientists believe that a quark star would have a slightly different mass and radius than a neutron star, and that future instruments might be able to detect this subtle difference. Others hypothesize that a quark star's birth would be so powerful that it would generate a quark nova, an explosion even more energetic than a regular supernova. Such an event would be so bright and so violent that we couldn't possibly miss it, and it would be the ultimate proof of a quark star's existence. These hypothetical objects are the holy grail of modern astronomy and physics. They are the ultimate test for our understanding of matter. If they exist, they prove that the universe has another level of complexity and extremity that we have only dreamed of. If they don't, then our current theories about what matter can withstand are correct. Either way, the quest to find them is pushing the boundaries of human knowledge. We have now traveled from failed stars and ancient relics to the ultimate extremes of matter itself, exploring a universe that is far more mysterious and magnificent than we could ever have imagined. And with every new discovery, we are reminded of one simple, humbling truth. The universe isn't a place of static wonder, but a living, breathing story, with countless chapters still to be written and countless stars still to be discovered. We have now explored countless hidden wonders, from the smallest planets to the largest structures, from the most violent events to the most ancient stars. Our journey has revealed a universe that is far more mysterious and magnificent than we could ever have imagined. And now, we must return home, but with a new perspective. We have traveled a long way tonight, together. From the cosmic rebels to the ancient relics, from the smallest planets to the largest structures, our journey has been one of discovery. We've peered into a universe far richer and more mysterious than the one we can see with our eyes. And as the night deepens around us, and the world begins to fall quiet, I invite you to reflect not on the grand violence of it all, but on the profound peace that lies within these hidden wonders. Think of the runaway stars, no longer as cosmic bullets, but as solitary wanderers on an endless journey, a quiet testament to their freedom. Think of the ancient relic stars, not just as fossils, but as the universe's quietest storytellers, whispering tales of a time before time. They are the elders of our galaxy, patiently holding the secrets of its beginning. The wonders we cannot see are a comforting reminder that the universe holds so much more than what meets the eye. The black holes, those ultimate secret keepers, are not just voids of darkness, but a canvas upon which the universe paints its most beautiful equations. The faint, ghostly whispers of gravitational waves are not screams of violence, but the final, silent symphony of two stars dancing their last dance. The rogue planets are not lost, they are simply home in the great, quiet, and beautiful emptiness between the stars. Think of it as a parallel to our own lives. There are so many things we know to be true, yet we cannot see them. The deep silence of a dark room, the loving hand of a friend in the dark, the quiet pull of a memory that brings a smile to our face, these are the hidden truths of our existence. They are the most important things of all, and they are defined by their very lack of noise and light. The universe, in its own way, is just the same. So as you prepare to rest tonight, I ask you to look out into the darkness and find a sense of peace in what you cannot see. The universe is not a chaotic, dangerous place. It is a vast and quiet place of immense beauty. The hidden wonders are not meant to scare us, but to comfort us, to remind us that there is always more to discover, more to learn, and that even in the quietest, darkest corners of the cosmos, something magnificent is always happening. The stars you see are just the beginning of the story. The rest of it, the most beautiful part, is hidden in the silence, waiting for you to dream about it. May you find peace in its light and comfort in its mysteries. Thank you, and good night.